afternoon, guys. Can you hear my voice? Am I audible, guys?
Yes, sir.
Yes.
Okay, we'll wait for 2 minutes, then we'll start the class. Okay? All right, let me share my screen and we'll start today's class. Is my screen visible?
Yes, sir. Yes.
Yes, sir.
Let me revise what we studied in the previous class about memory management. Then we will continue today's class. So we thought of memory, main memory, how memory is a central part of operating system, and it is handled by the although we have the memory as a hardware, which is a large array of bytes with its each address. Um, when an instruction is fetched from execution to the CPU, it is taken from memory and it is computed its operations and kept back in the memory again. Okay, the main memory and the registers were directly accessed by the CPU, and we try to understand that the main memory can be having two processes, two important. The space can be divided, one for operating system, other for the user processes, and each process we will allocate a separate memory, and based on the memory required for a particular process, we will decide the base address and the base plus limit address. In that particular location only the process will be legally all the addresses is allocated legally with that within the given process only. So we will check when an CPU generates an address, that address should be greater than or equal to base address, and it should be less than base plus limit address. Then only for that particular process that memory location will be allowed to access. In order to avoid the operating system processes or some other user processes, in order to protect that, we are maintaining this base and base plus limit and verification. So we also try to understand the address binding, how it happens when a program is converting at a compile time and load time and execution time, how the memory is allocated using this CPU address and physical address. There is a memory management unit that converts logical address that is generated by CPU into a physical address which is actually map, uh, which is actually the physical memory location that is where the data is stored, and the runtime mapping from virtual to physical addresses is done by a hardware called memory management unit. So we also try to understand that when you want to allocate the dynamic relocation register using a relocation register, this relocation register will contain the address, and CPU generated the address. If you add, this will give you the physical address. And as I told, that memory is usually divided into two partitions: operating systems and the user processes. Usually the memory is kept in a continuous memory location, that due to many decisions the operating system is kept at the higher memory, and the remaining memory is used for the user processes. Okay. Now we also try to understand how memory will be protected using limit register and relocation register by verifying the condition the logical address is less than the limit at the limit register or not, and once it is less, then we will add the relocation register to access the physical memory. And we also try to understand that once the process is occupying the memory, and it will look like a large hole, and once the process gets occupied, when there is no memory, they will wait, and once the process leaves, then it will create a hole. Then this memory is allocated to some other processes, and they will come and take place, and some process may leave, that will create a lot of holes. And in continuous memory location, when you are allocating one process after another, this happens. Now when you are creating a lot of holes, then when a new process is coming, how we can allocate the dynamic storage location problem is using three strategies: first fit, best fit, and worst fit. So we try to understand with an example. First fit is like allocate the first hole, best fit is like allocate the small hole, worst fit is allocate the large hole. And we try to study this continuous memory allocation with first fit method, best fit method, and worst fit method with examples. And this methods will create some space unused that is left out, which cannot be used. For example, in this worst fit, block 1 is taking worst fit method, you have to allocate the large block. So job 1 will go and take the block 4, which will leave the 190 kilobytes space unused. Although we have job 4 with 70K and we have memory 190K, still we will be not able to allot because this block 4 is been already allocated to job 1. So we have memory, but we will be not able to allocate. And job 1 needs only, sorry, this is 10K, right? This should be, job 1 is only 10K. So this 10K only needs, job 1 is only 10K, but this 200K is left unused 190K. We call that as an fragmentation. This is called as an external fragmentation, where a block, you can say that when you allocate a block, suppose you have a block and you use, this is a block 4, let us say that this is block 4, this entire block will be taken by one process, and you allocated only 10K of some space and remaining all this space left unused. This is called external fragmentation. Okay, this is called external fragmentation. However, suppose a process is allocated say 10 kilobytes, but in the 10 kilobytes it may not completely used all the time 10 kilobytes. For example, in this particular job 1, in this process 1, suppose you declared array of an array, you declared array of say a of 50. Now this array 50, when you declared, the memory will reserve this 50 locations, but you may use it or you may not use it. So although the memory declared suppose 10K, suppose you declared 10 locations, now these 10 locations may be used or may not be used. Suppose you are using only 5 units and remaining 5 units are unused inside this allocated memory for a particular process. So this is called internal fragmentation. Okay, internal fragmentation. You understood what is external fragmentation and internal fragmentation? When you allocate for a particular process, inside that process, the memory unused is internal fragmentation. The memory is allocated in a particular block and the unused space is called as external fragmentation. Is this clear?
Yes, sir.
So we discussed that in previous class. Now let us continue our discussion in today's class, memory management part 2. So we stopped at allocating the memory in first fit, best fit or worst fit. So this will create us fragmentation and we have to deal it because there are, although we have processes and we are not able to allocate, that's a big problem. So fragmentation can be either internal or well as external. External fragmentation exists when there is enough total memory space to satisfy a request, but available space are not continuous. If they are not continuous, we cannot allocate it. So that's the main problem where the external fragmentation is created. Storage is fragmented into large number of small holes. This fragmentation can also be severe. Both first fit and best fit strategies for memory allocation suffer the external fragmentation. We could have observed in the previous examples, you can see that the best fit and the first fit also suffer from external fragmentation. There are some unused space in first fit and best fit strategies also. Statistically, the first fit, for instance, reveals that even with some optimization, given n allocated blocks, another 0.5 allocated blocks will be lost to fragmentation. That is, 1/3 of the memory it is used unusable. This property is known as 50% rule. Okay, usually statistical analysis, because after observing so many processes allocating with this memory locations, it is observed that of n allocated blocks, 0.5 n blocks will lost in fragmentation. So 1/3 of the memory, because some part of the memory is allocated to the operating system, and of the available memory, only few percent, 0.5, 50% of the blocks are allocated. That is a statistical analysis, which is called as 50% rule. Now, for internal fragmentation to understand, when we are creating multiple partitions and we will create a whole, say for example 18,464 bytes. Suppose the next process requires only 18,462 bytes. We allocate exactly the requested block and we left with whole of 2 bytes. The overhead to keep track of this whole will be substantially larger than the whole itself. The amount of overhead to keep tracking the whole and for the allocation for the requested block itself is overhead. So we will, when we are creating multiple partition, keeping track of all the holes where this process will fit it, which place itself is an overhead. So in other words, if we are going for non-continuous memory location, then that will also be a creating problem. So the general approach to avoid this problem is to break the physical memory into fixed size blocks and allocate the memory in its unit base. Instead of going for continuous variable sized memory, you divide the memory into fixed block size and allocate the memory. Suppose this memory, every block in the memory is divided into, say 100 bytes, 100 kilobytes, and if this is the problem, every process will be 100 kilobytes. Okay, now when this approach, the memory allocated to a process might be slightly larger than the requested memory. Suppose if your process is 50, still this will be allocated. If it is your process is 100, still this block is allocated. If your process is 5k, still another 100k. All memory partitions are fixed size. To avoid this approach, fixed size blocks allocate the memory based on the block size. Then that will also create a problem. The difference between these two numbers, like how much of allocated space, unused memory in the is considered as the internal partition. Okay, internal to a partition. So this is called internal fragmentation. Internal fragmentation is you allocated some memory. This process will take entirely up to this fixed size. Now this will also create some overhead, that we call that as an internal fragmentation that I explained in the in this case. For example, each hole, multiple partitions of every hole is one. This block is consists of 18,464 bytes, but we need a process only 18,462 bytes. This 2 bytes is called internal fragmentation. This will create a whole of two bytes of internal fragmentation. Okay, so the fixed size blocks will also create some fragmentation that is called internal fragmentation. So one solution to the problem of external fragmentation is compaction. Compaction means we will shuffle the memory contents so as to place all the free memory in one large block. Means, for example, we allocated some process P1 here and some, this is free space. Again, we allocated P2 here. This is taking some memory space P2. Now, what compaction says it, you move all the process to one end. Okay, relocation of all the process to one end. The goal is to shuffle the memory contents to all free memory will be together. So this free memory will come and stay here. So this will look like this. So we'll have an operating system. Maybe the process P1 will be here. We will shuffle this, we'll reallocate this memory, and we will bring down this free space here, and this free space will continue up that. So this is called compaction. We will shuffle the memory content so that the space in between will be, we will relocate that and kept it where we can see that as a one large block. If the reallocation is static, which is done at the assembly or load time, compaction cannot be done. If it is possible only, it is possible only when the reallocation is dynamic and done in execution time, because during the compile time or the load time, the memory is pre-allocated. Once it is pre-allocated, you cannot shuffle it, you cannot move it, because that will create a lot of issues. But if the memory is allocated dynamic at the execution time, which is done at the execution time, then the memory is still not allocated, then we can reallocate the memory before compiling. Means at the execution time we can allocate the compaction. At the static allocation we cannot carry out the compaction. The simplest compact algorithm is to move all the process towards one end of the memory. All the holes move in the other direction, producing one largeable hole of the memory. This scheme is very expensive, because reallocating the memory for a particular process, you have to update all the registers, program counters, a process control block, all this information you have to update it. This will be very expensive. So compaction could be one solution to fragmentation, but this is very expensive solution. Is this clear up to this point?
Yes.
So to overcome this fragmentation, people come up with a new concept called paging. So paging is a memory management scheme that permits a process physical address space to be non-continuous. Okay, the paging will help us to handle the memory management of a physical addresses, processes physical addresses space to be non-continuous memory location. Now, the part of process can be allocated at one place, the part of other process can be allocated at other place. Paging avoids external fragmentation and associated need for compaction. So two problems that plague continuous memory location. The external fragmentation that will create will be addressed, and also compaction, it is not required. Paging avoids these two issues. Because it offers numerous advantages, paging in its various forms is used in most operating systems, from large servers through the small mobile devices. Paging is a memory management scheme that will help us to handle the external fragmentation and compaction in all the computers now we are looking today. In all the operating systems this has been used. Paging is implemented to the cooperation between the operating system and the computer hardware. We need to have the cooperation between the operating system and computer hardware, and let us try to understand how paging is done by the operating system. Paging is a memory management scheme that permits a physical process address space to be non-continuous. Means it will be not in continuous allocation. Paging avoids external fragmentation associated for compaction. This is already we studied. We studied in the previous slide. Okay. So the basic method for implementing paging involves breaking the physical memory into fixed size blocks called frames, breaking logical memory into blocks of the same size called pages. So the paging divides the physical address and logical address into frames and pages. Every address that is generated by CPU is divided into two parts, a page number and a page offset. So when a CPU is generating some address, it will generate in terms of the page number and the page offset, P and D. Now, this P and D, when CPU is generating some logical address, this values will be looked into a page table. This is a page table, which is a paging hardware. Now, this particular value of P, the page, whatever is generated by CPU, for the particular page, a frame, which is located in the actual memory. In physical memory, we call that as a frame, frame E, frame F, frame G. CPU generated, we call that as a logical address. This D value is same, but the page is converted into frame using a page table. There will be inside a page table that will make the mapping from pages to frames. So pages is belong to CPU table, frames belongs to the physical memory. This page table will handle the mediator between the logical address space and the physical address space, and it carry out the when this happens, this F can be allocated wherever the F is there, it will go directly access the memory. There is no wastage of space. Now the page number is used as an index into per process page table. The page table contains the base address of each frame in physical memory and the offset of the location in the frame that is being referenced. Thus base address is the frame is combined with the page offset and defined the physical memory addresses. So D is an offset which does not change. It is not replaced. Red or frame number and offset number comprising the physical address. So this is very important. Offset is D. So we have two components in paging, page number and page offset. This offset will help us to track down all the page addresses and that will create an offset. For example, we'll study one example. Here we'll see one example. But before going an example, we have to understand that how memory management will take care of paging. The following units, the steps by the memory management unit will take place for the paging to translate a logical address generated by CPU into a physical address. Generate the physical page number P and use it and index into the page table. Whatever the page number P is generated, that is looked into the page table. Extract the corresponding frame from the page table F. Reference the page number P in the logical address with the frame number F. So we have a page number, we have a page table. This page table is a reference that is mapping to for the particular page the frame, and the frame number is used for this particular page number. So this is what replaces the page number P by logical address of within the frame. Now let us see that one example. Suppose we created CPU generated 4 pages, say 0, 1, 2, 3, and this 0, 1, 2, 3 in page table is stored at this location. 0 page is stored at first location, first page is stored on fourth location, page 2 is stored on third location, and page 3 is stored on third location with memory 7. Now this is a frame number. The frame number tells that the page table tells the relationship between page number and frame. So page 0 is kept at frame 1, which means that it will go to frame number 1. It will see that page 0 is accessible. Frame 4 is kept on page table 1. So if you go to 4, you will find the page 1. You go to 4, you will find the page 1. 2 in 3. If you go to 3, you will find page 2. Likewise, 7 is kept at page 3 is kept at frame number 7. So go to frame number 7, you will get the page 3. This page table will act as a lookup table to map between the page number and the frame number. Is this clear? We have a logical memory, we have a physical memory. So this memory locations are not continuous. You see page 0 followed by there is a memory gap, page 2, page 1, page 3. Now there is no external fragmentation. The complete space is occupied because we divided this physical memory into frames. Based on the page number and the frame details, the page lookup table will act as a mediator that will help you to put which page will go to which frame. Is this clear?
Yes, sir. Sir, what was that D part in that diagram before?
We will see that. Okay, I will tell you one more example. Now, suppose let us say that here the logical address n is equal to 2. Okay, and m is equal to 4. Now with n is equal to 2, m is equal to 4, the page size can be, using a page size of 4 bytes, the physical memory can be 32 bytes because n is equal to 2, 4 bytes means we can have a physical memory of 32 bytes. 32 bytes. Okay, that is how, because of 2 to the power of 4, n is equal to 2. With each page 4 bytes, we can have maximum 32 bytes, that is 8 pages. Okay, now let us say that the 8 pages are these locations are divided like this. Now this 32 bytes are stored in 8 pages like this. Okay, now this 32 bytes of 8 pages, let us say that 0 is stored a, 1 for, this is the page number and this is the some information. Now this is entirely, we call that as, this is entirely called that as a page 0. Okay, or we can say that this is, let us say that this is, let me do one thing, let me try to make understand even in a better clear. Suppose let us say that you have 16 elements. Each element is divided into 4 blocks because we say that m is equal to 4. We divided m is equal to 4. Now we have a page table. In this page table we have this reference 0 is located, 0 page is located in page number page table, that is 5. Okay, now how we will calculate is like, let me take the pen. Now the logical address for 0, that is for a, is 0. Okay, so we will calculate 0, the index, the page is 0, offset is 0. So we will come and calculate the table. In the index table, page table, we will find the 0 is in the frame 5. The 0, this is page 0. Let us assume that this is page 0, this is page 1, this is page 2, this is page 3. Okay, we have 1, 2, 3 pages, 0, 1, 2, 3 pages. These are frame numbers. This is a physical memory, the memory in which you can allocate in a non-continuous form. We are not allocating in continuous, see, we are allocating randomly. Now we are allocating at any place, and but we are making a reference of frame number. Suppose let us say that ABCD is allocated in 20th frame. Okay, now this frame number 1, 2, See, this is frame number 1, like how I kept page 0, page 1, page 2, page 3. Likewise, I'm keeping frame uh, 0, 1, 2, 3, 4, 5, right? So this is frame 0, this is frame 1, this is frame 2, this is frame 3, this is frame 4, this is frame 5, frame 6, and frame 7. Okay, so let us say that we have 7 frames. Now, this is a page table, that is a lookup table. When it says 5, means page 0 is stored in frame 5. Okay, so page 0 is stored in frame 5. Page 1 stored in frame 6. Okay, page 1, that is EFGH, is stored in frame 6. Uh, frame 2 is stored in, page 2 is stored in frame 1. Let us say that page 2 IJKL is stored in frame 1. So 2 is mapped to 1. And likewise, 3 is mapped to 2. So page 3 MNOP is mapped in second frame. Okay, so we mapped this. Now let us try to calculate a particular value. Suppose I want to see that where A is stored. Where A, that is generated by the logical address, I want to see that where this A value is stored in the physical memory. Now how I'll do that is a simply formula of calculating the offset. For A value, the address is 0 and the frame, the index of the page table, and we find that it is in the page 0. So this will go and find, this is in page 0, it will go on page 0, find the frame 5. So we have to calculate it is in the frame 5. Then the logical address mapped to physical address simply by multiplying the values of the frame number and the value of M multiplied by the offset value. Okay, so 5 into 4, 20. So 20th location A is stored. Here it starts with 0. Let us take another example. Let us take one more example. The logical address of 4. So the logical address of 4 is this E value. Okay, the logical address of 4 here is E. Now what we will do is, logical address of 4 is in page 1. This is in page 1. We will take the offset is 0 because it is in the first element. Okay, the offset is in 0. Now according to the table, page 1 is mapped, P1 is mapped in the frame 6. So the logical address is mapped 6 into the M value 4, that is 24. You see the 24th location E is found. Okay, 20 E, which is kept in page. With this simple conversion, we can calculate into the physical address. Now let us take another example. Let us take that 13, the 13th memory location. Here this page number is 3 and the offset is 1. Okay, here the offset is 1. So the page 3 is mapped in location 2. Okay, this is location at 2. So 2 into 4, this will become 8. This will, the logical address of 13 is calculated. The page number 3 is stored at 2. So 2 into 4 plus the offset value. The offset value is 1. The offset value here is 0. The offset value here is 1. Offset value is 2 and offset value is 3. That will be for each page. The offset value here is 0, 1, 2, 3. Here the offset value is 0, 1, 2, 3. Again the offset value is 0, 1, 2, 3. Now for this 13th location, the offset value is 1. Okay, so 2 4s are 8, 8 plus 1, 9. At the 9th memory location, 8. Here also the offset is 0, 1. This is 8 plus 1, 9. So this is continuous memory location. Okay, 0 to 4, 4 to 8, 8 to 12, each memory locations. So the ninth memory location is this. The n is stored. See, the n value which we are storing is stored exactly at the ninth memory location. You can check any value. Let us check this k is equal to 10. Okay, the offset value here is 2. Offset value is 2 plus this P2 is stored in 1. 1 into 4, 4, 4 plus 2, 6. K is stored at 6th location. 4, 5, 6. 6th memory location, K is stored. You understood the mapping?
Yes, sir.
So the paging will help you to map a 32-byte memory with 4 byte pages. This is a 32-byte memory. How many memory locations you have? 0 to 28 plus this is 4 locations. So 28 plus 4, 32-byte memory locations. This 32-byte memory locations we stored in 4-byte page. This is 16 bytes. That is indirectly 4-byte pages. But actually, how many pages we can fit in this? How many pages we can fit in this 32 frame physical memory?
8.
1, 2, 3, 4, 5, 6, 7, 8. That's what we told. Using a page size of 4 bytes, using a page size of 4 bytes with a physical memory of 32 bytes, we can store 8 pages. Okay.
Yes, sir.
So this paging is fully occupying all the space. There is no fragmentation. There is no unused space. It eliminates the fragmentation. Do you observe any unused space?
No,
So
sir.
there is no need of unused space. I mean, there is no unused space also, and there is no compaction. We are not moving all the process blocks at one end. We are not moving all the free blocks at the other end. We are allocating as it is, but we are maintaining an intermediate block called page table. So we are mapping using this page table from the pages to the main memory locations. The main memory locations, we call that as the frames. The logical memory that we generated, we call that as the pages. In between this page table, we are maintaining the relationship between the frames and pages. That's what we studied here. Okay, we have a page number and page offset. So whenever we are coming with a page number and page offset, see, when a page 0, we have 4 elements. This elements needs the page number also and the elements 0, 1, 2, 3, 4. That is called offset. A page is divided into page number and the number of elements in that page. That we call that as an offset. Is it clear?
Yes, sir. Clear.
Now, likewise, in the frame side also we have offsets. So that's what we have written here. When a CPU is generating a logical address, it will generate a page number and the offset value. The offset value is the same at both logical address and physical address. The offset D value will be the same. Whatever it is generating at the logical address and the physical address, the offset value will be the same. Suppose you found it here, A at the first position, you will find A only in the first position itself. You find G in the second offset, you will find G in the second offset only. Okay, the offset is same in pages and frame. What changes is the page number. Page number to frame number will vary. That's what we are maintaining. Only the page to frame information we are maintaining. So the page will look to the page table. It will look for the corresponding frame. It will go to the corresponding frame and it will look for the particular frame. Okay, so this is the page table which contains the information which page is in which frame. Is this make sense? Now this diagram is making sense.
Yes.
Okay. Now this is the
Sir,
offset. So yeah.
sir, will the size of page and a frame will always be same, or it can be
Page.
different?
No, it's different, no? Here, how many bytes are you using?
Sir,
This 4
we are
bytes.
using for 4, and for each frame we are using 4.
Yes,
Sir, in
that
this
should
case
be
it
same.
is equal, but
Here,
it can be
here,
different or no?
no. In different also, in reality also, it will be the same.
No, okay,
The
sir.
offset is same. The offset is same. D is same here. Okay.
Okay, sir.
The offset D does not change. It is not replaced. The frame number and the offset comprise the physical address. Okay. So the 3 steps that are followed here is extract the page number, use it as an index into the page table, extract the corresponding frame number from the page table, replace the page number P in its logical address with the frame number F. So we have to maintain this information. Okay, if I have to explain in detail, this is the idea. Okay, now when we are using a paging scheme, we have no external fragmentation. Any free frame can be allocated to a process that needs it. However, we may have some internal fragmentation because when frames are allocated as units, if memory requirement of a process do not happen to coincide with the page boundaries, then it may not completely full. For example, suppose if a page size is 248 bytes and a process needs 72,766 bytes, how many memory locations will need? If you divide this, you will get approximately 35 pages and 1086 bytes. If you allocate the 36 frames, the one more frame if you allocate, then 2048 minus 1086 will leave you 962 bytes. If you allocated the 36th frame, resulting in an internal fragmentation, because each page size is 48 bytes, and this process needs this many memory locations, 72,766. The number of pages you will allocate will leave us some internal fragmentation. So suppose in this example, there is another say fifth block and you have only two elements, 16 and 17. Suppose if your process needs 17 memory locations, then this page, let me redraw it. Suppose in this example, you have another page of, if you have to take 4 bytes, but the process needs only two locations, 16 and 17. Your process needs only 17 locations. So you have to create one more location for page, maybe page 4. Page 4 will come, maybe you allocate it somewhere. This memory, what you are allocating, when you are allocating this letter and this letter, this will be allocated, say it is allocated at frame, this is 0, 1, 2, 3. Suppose let us say that this is allocated at frame 3. Now you have allocated two memory locations. Your process is having 17 memory locations. This two space will be gone in waste. That is called internal fragmentation. Okay, so you have process of 72,766 bytes, and suppose each page size is 2048 bytes. We need to allocate 36 frames, but it will leave 962 bytes unused. We have to allocate 36 frame because of 1086 bytes. That will leave us internal fragmentation. Although paging takes care of external fragmentation and compaction, paging may result in some internal fragmentation. In worst case, the process would need n pages plus 1 byte. Then it would be allocated n plus 1 frames, resulting in internal fragmentation of an entire frame. This could be possible. Does this make sense?
Yes, sir.
All right. So let us now proceed further. So frequently 32-bit CPU, each page entry 4 bytes long, but this size can vary. Okay, when size is varying, then the page size will be the same. Suppose you are keeping 8 bytes, then each page size will be 8 bytes only. If you are keeping 16 bytes, then you can keep 16 bytes. The 32-bit entry point, one of 232 physical frames, page frames can be possible. So if the frame size is 4 kilobytes, that is 2 to the power of 12, the system with 4 byte entries can store addresses up to 16 terabytes of physical memory. So 2 to the power of 44. Memory locations in physical memory can be handled with simple 2 to the power of 12 byte size. Okay, does that make sense? If the frame size is 4 KB, then with this 4 KB information, we can able to access the physical memory of 2 to the power of 44, because 4 KB is 2 to the power of 12, 2 to the power of 44 is 16 TB. 4 byte entry in each table will take you to 2 to the power of 44 addresses. Shall we go ahead? Okay.
Yes.
Now let us see. Now let us see that this is one example. Suppose this is the free frames. Okay, when a new process is coming, um, these are free frames. These are all free frames. So there is no pages allocated here. These are all free frames. A tells us before allocation. Okay, this is the part of A. This is the A part. Now we have free frame list 14, 13, 18, 20, 15. So 20 frame is free, 13, 18, 20, and 15. So these are the frames, free frames. We have pages 0, 1, 2, 3 for a new process. Now we will allocate them one after another. Suppose we will create a page table, and page 0, let us say that it is stored in 14. Okay, page 0 is stored in frame list 14. Page 1 is stored in frame list 13. Page 1 is stored in 13. Page 2 is stored in 18. And page 3 is stored in 20. Okay, the new process page table is created, and this is allocated to particular location. So 0 is allocated to page 14. Okay, 0 is allocated to page 14, 1 is allocated to page 13, page 1 is in 13 frame, page 2 is in 18, 18th page is allocated to page 2, sorry, 18th frame is allocated to page 2, 20th frame is allocated to page 3. Okay, this is how. Now the frame 15 will be empty. When a new process is coming, if you want to take it, it will allocate it. So the free frame list is maintained. When a new process is coming, this many page locations if needed, it will allocate based on the free frame list. It will allocate the memory. Okay. Usually the paging happens like this. So every time after finishing this process, this page information will be available in the free frame list. This is the free frame list. After the job is done, after this process finished, these free frames will be added into the free frame list. When a new process is coming, it will say that this many pages I want, then again it will be allocated those many frames. Okay, you understand how operating system handles the memory allocation for a particular process using paging?
Yes, sir.
Okay. So before looking into translation look aside buffer, let us take break. It is 3:50 now. We will take 10 minutes break. Then after break, we'll continue. If you have any doubts up to this point, please ask me. Otherwise, we will take a break of 10 minutes. We'll come back at 4 o'clock. Okay, shall we get back?
Okay, sir.
All right. So let us continue our discussion on memory management. Suppose we want to access a location I, we must first look into the page table, and we have to look to the page table offset for the page number I. So this requires one memory access, right? We are storing the page information and whatever the page number. Then we have to look into the process page table. This requires one memory access. It provides us the frame number. So this page information will give you the frame number. This frame number, again, we need to, which is combined with the page offset, is the actual address. So we can now access the desired place in the memory. With this scheme, two memory access are needed to access the data, right? First, we have to look into the page table, then we have to look into the particular frame, then we have to look into the page number, frame number. So first it will come to the page number. Whatever the page 0, it will look into the frame. That will take one memory access. From here, again, it will go and look into the frame number. That will take the two memory access. So this is the same for every value. So with this scheme, usually two memory access are needed to access the data, one for the page table entry, other for the actual data. Memory access is slowed by factor 2. So there is a delay in considering the intolerable under most circumstances. These examples will give us two memory access. So instead of accessing one memory location, now we are accessing two memory locations. That is the main disadvantage of paging. Now, to address this two memory access, we can improve that to a slight, not completely, but to a better way using translation look aside buffer. So the standard solution to this problem to avoid this two memory accesses every time. Okay, not every time instead of two memory accesses. Sometimes we can decrease in a direct hit. Okay, so to use a special small faster looker hardware cache, so we will keep one more buffer uh, in between the memory access and the frame number. We call that as a translation looker set buffer. It works like this. So it works like this. So what happens here is paging is there with TLB, translation looker set buffer. So when a CPU is generating a logical address, it is generating with page number and the offset. So this logical address is mapped to page table, will give you the frame number, and you will take the physical address, access the physical memory. But there is a TLB, translation look aside buffer. In that, we will keep some important information with direct reference of page number and frame number. So what happens here is when an address is generated for a particular page number, it will go directly. First, it will come to translation look aside buffer. This details of page number, frame number, it will come. If the page number is there in this table, in this buffer, you will get the frame number. It is a direct hit. So it will go to the direct access. Without accessing the page table entry, without searching this page table entry, the direct page number and frame number will be kept in translation look aside buffer. So first, when a CPU generates the logical address, it will search the translation look aside buffer. It will calculate the page number and frame number. If it is a TLB hit, it will directly access the memory. If it is a miss, if TLB miss, then it has to search the page table. Then this page table, you will find the frame number. After that, it will access the address. Now, translation look aside buffer is associative high speed memory. Each entry in TLB consists of two parts, a key and a value. Okay, So this is a page number, a key, and a value, a frame number. When an associative memory is presented with an item, the item compared with all the keys simultaneously. If the item is found, the corresponding value field is returned. The search is fast. TLB lookup is a modern hardware which is a part of instruction pipeline. So there is no essential adding, no performance penalty is there. So um, so this is a high-speed associative memory buffer which is added to decrease to memory access, uh, and sometimes it will avoid the delay. We can directly access the memory. Is this clear by how TLB works? Why TLB is coming?
Sir, by TLB, we don't have to find the frame in this page table. Na?
No, no, no. You no need. It will give directly the frame number.
Okay, sir.
So it's a direct hit. But if the page number after searching in this TLB, if you couldn't able to find the page number, then it's a miss, TLB miss. Then you have to come and search in the page table. Suppose you found the page number, then it's a TLB hit. You will get the directly frame number. You will access the physical address. Is it clear?
Sir, if a page is associated with the frame, then shouldn't be it in TLB also?
No, this is a small space. This is a
Okay.
small, all the page information will be not kept in TLB.
Okay, sir.
Only few, only important applications where it will not cause delay much. Those only we will keep in the TLB. Okay. So TLB contains only a few page table entries, not everything, not all the page. Then that is more or less equal to page table only. Suppose in page table, let us say that we have 32 entries. In page, say, let us say you have 6 or 5 entries. Okay, instead of searching 32 frames, you can search only 6. If the 6 is got hit, you got directly the frame number. It will delay the access time, right? If it is missing, then you come and search in the page table. In the worst case, this page table could be large size. This TLB is very small size. So TLB contains only few page table entries. When a logical address is generated by the CPU, memory management unit first checks the page number is in the TLB or not. If the page number is found, frame number is immediately accessed. It's available to access the memory. Okay, as just mentioned, these steps are executed as a part of instruction pipeline within the CPU. So when an instruction, you studied computer organization, you got a subject called computer organization.
No, sir.
So what happens in when an instruction is executed in a pipeline, there are a lot of steps involved. Okay, when a process, when it is executing by the processor, you can search the pipeline, CPU pipeline, how a process is executing. So even in execution of process, uh, it will create lot of time. Okay, so if I have to explain that, that will take a lot of time to explore that. Maybe in the next class, I will tell you that. Is that okay? What are the steps that are involved? That will take a lot of time, but actually, it will be taking less time. So suppose, okay, let me say now only. There are four stages when an CPU is executing some instructions. Okay, one is uh, instruction fetch. It will fetch from the memory. Stage 1 instruction will be fetched. Then this instruction will be decode. What is the actual meaning of this instruction? It will be decoded. Then it will execute. Then the memory will be accessed. Okay, after memory access, we will write it. The fifth step is we will write. Okay, this will happen one after another. Suppose when an instruction is coming first, it will fetch the instruction, then it will decode, it will execute, it will access the memory. There are, then it will write it. There are 5 stages. So when an instruction is pipelined, while the instruction is fetched, while the CPU is decoding, while it is executing, there are many stages involved in a CPU instruction cycle. Meanwhile, this TLB can be verified. This translation lookup table can be verified. The steps, when process is executing the steps, TLB operating system will take care of the TLB access with no additional penalty. The performance will not degrade that much. Means when an instruction is executed in a pipeline, there are many stages. So looking into TLB will not create that much difference because we are keeping only few page table entries in TLB. Maybe when you study the computer organization or digital computer organization in the coming semesters, you will understand how a processor will execute instructions. There are many stages involved. So because of this pipelining stage, adding a TLB will not create an extra additional performance penalty compared to the system which does not implement paging. Okay, so this is very fast, that's why. So if the page is not in the TLB, address translation proceeds the following steps. Then the memory references table must be made. So when the frame number is obtained, how earlier that how a page frame is, it will look into the page table, then it will get the frame number. When the frame number is obtained, we will access the memory. If in addition, we will add the page number and the frame number to the TLB so that they will be found quickly on the next reference. If TLB is already full entries, then existing entry must be selected by replacement, right? Suppose you have here only 6 entries are there. Now, suppose a new entry we need to keep in the TLB. How we will decide? Suppose how many locations are here? 1, 2, 3, 4, 5, 6, 7 locations are there. Okay. So suppose now we have 7 locations. Now suppose eighth one more entry we have to make in TLB. Now we can't do that, right? Because this is full. If we have to keep the 8th one, we have to replace one of these entries. How you will replace it? Which one you will replace it? That is again, it will create a lot of questions again. So which one we will replace is, we will replace which is least recently accessed. Means we are, when a CPU process is creating a logical address, suppose 1 is now accessed, 2 is accessed, 3 is accessed, 4 is accessed, 5 is accessed, 6 is accessed, 7 is accessed. Now which is the last, then one more second time, again 1 is accessed, 3 is accessed, something like that. When a CPU is generating and looking for the TLB, it is verifying the page number. Some entries will be least accessed, some entries will be most frequently accessed. Whichever the entry which is least referred in the TLB, that reference will be replaced by 8. Suppose 7, every time it is coming, 1 is referred say 3 times, 2 is referred 4 times, 3 is referred 6 times, and 4 is referred 8 times, and so on and so forth. 7 is referred only 1 time. So this entry is only 1 time hit, and 1 time only it is referred. This entry is not to be fit in TLB. So maybe 8 instruction is loaded here, and we will observe, we will keep track of every hit. Whenever there is a hit, we will keep a count, and whichever is the least count, we will keep replacing by the new entries. Is that clear?
Yes, sir.
So the replacement policies can be ranged from least recently used through round robin. You can say that round robin means like now 1, 2, 3, 4, 5, 6, 7 is there. First replacement you do with 1. Now after nine process is coming. Now 9th replacement will be done by 2. Now 10th is coming, 10 by 3, 11 by 4, 12 by 5, 17 by 6, 18 by 7, then again round 19 by 1. You can replace one after another also, or you can replace which is least recently used. Round robin, you no need to maintain any counter. Least recent, we need to maintain the counter. So that is again an additional charge. We can replace the TLB with full of entries. When new entries need to be done, replaced, you can follow any strategy. Now, the percentage of times that the page number of interest is found in TLB is called a hit ratio. Okay, the percentage of times a page number of interest is found in TLB means TLB hit is called as an hit ratio. An 80% hit ratio, for example, means that we find the desired page number TLB 80% of the time. So if it takes 10 nanoseconds to access memory, then a mapped memory access 10 nanoseconds when a page number is in TLB, right? So I mean, if it takes only 10 nanoseconds to access the memory, if that uh, if that memory mapped access is in TLB, total memory access for the TLB will be, see, total memory access for a particular uh, value, if it is in TLB, is the same as the total memory, right? Suppose the memory access takes 10 nanoseconds with the page number, then the total memory access will be 10 only. If you fail to find the page number in TLB, then we must find across the memory page table entry and the frame number. So let us say this takes another 10 seconds, then access the desired byte in the memory takes 10 seconds. So 10 plus 10, it will take 20 seconds. If it is TLB hit ratio, then it will be only 10 seconds. If it is a fail, then the page table entry say 10 seconds, then the another memory location 10 seconds, it will take 20 nanoseconds. So the effective memory access time we can calculate by its probability by hit ratio 80% of the time, 0.8 into, because this hit ratio it is in TLB, this TLB takes only 10 nanoseconds, 0.8 into 10. If it is not in TLB, then it will take another 0.20 by 10 plus 10, 20 nanoseconds. So this will take 12 nanoseconds only. This is very better. Otherwise, if it is not in TLB, if you don't keep in TLB, then for each and every page number, you have to access 10 nanoseconds. This also 10 nanoseconds. So the effective access time will be 20 nanoseconds for every time. Now, because of this TLB, we decrease the effective access time to 12 nanoseconds. So there is 8 nanoseconds difference. Is this clear?
Yes, sir.
Because of TLB, we are decreasing 8 nanoseconds. Okay. So in this example, we suffer only 20% slowdown on average memory access time from 10 to 12 nanoseconds. So 99% hit ratio means it will be more realistic. We have only 10.1 nanoseconds. So the increased hit rate produced by 1% slowdown in that access time. So this is very advantage. Translation local site buffer will increase the effective access time. Okay. So there is another concept called shared pages. Shared pages helps us to standardize the paging environment. Suppose let us say that a process P1 is using the library 1, library 2, library 3, library 4, and so on and so forth. So this process P1 is keeping the page table P1 3, 4, 6, 1 like this. Okay. So process P1 page table 3 is located in the physical memory, and process page 2 for library 2 is located at 4. Process P1 third uh, third reference is kept at 6. Sixth location library 3, and so on and so forth. Now let us say that process P2 is also using some standard C library, This is also maintaining another page table. Process P3 is also using some another C programming. This is also maintaining some library, and this is also maintaining page table. Now each process is maintaining its own page table and the reference, right? The physical memory. Now, ideally, what will happen? This page table references can be located at different memory locations for process P1. This main memory can be allocated different page tables for process P2. These locations can be assigned at different memory locations for process P3. But because they are using the same libraries, they are shared for all the process. So library 1, library function C, libraries programming C4, they kept in one memory location. These memory locations are shared to all the process in the page table. You see this page table 3461, 3461, 3461 says that these memory locations you can access these files. So these files which are stored only once, but it is shared. These memory locations are shared to 3 processes. This is called a shared pages. Is this clear? Ideally, for this each process P1, if I have to allocate the memory, this will take 4 memory locations, right? Assume that this will take 4 memory locations. This will take 4 memory locations. This will take 4 memory locations. So total, I have to allocate 12 memory locations. Then the page table entry will be unique. The memory will be occupied by 12 memory locations, and the page table entry will be different. Now, but they will be repeating. The same libraries are repeating at different memory locations. If we are able to manage the sharing of the standard C library in the paging environment, then that memory locations, instead of copying at multiple places, if we can able to keep at one place, the same memory location will be provided to all these pages, then we can call that as a shared pages. Is this clear?
Yes.
There is different ways we can structure the page table. So for example, there is a hierarchical paging. So in hierarchical paging, what we will do is we keep 2 page tables, a 2-level 32 paging architecture. So we have an outer page table, we have a page of page table. We can see this is the main memory location. Main memory location. This is the logical address. P1 is hit here. Okay, then P2, based on this location, P2 is calculated in this page table. Then D is calculated as per the offset. It is computed. So first P1 is looked in the outer page table where it is a particular hit. Then P2, when you keep such kind of outer page table and page table of page table, we call that as a hierarchical paging. For example, like this, an outer page table which will keep this entry will keep up to 1 to 500. This entry will keep 100 to 708, and so on and so forth. So this is an outer page table keeping track of another page table. This page table will provide from 928 to 900. Again, there are so many memory locations. So it's called a 2-level page table scheme. A 2-level page table or a hierarchical page table, we can make another page table for the page table. That will be our outer page table. Okay, and you can access the memory. Is this clear?
Sir, in this, the memories are overlapping now. So how it is useful?
No, not overlapping. I'll tell you for this example. For example, in this case, okay, so we are creating a page table here. This is the frame. This is the page table, right?
Yes, sir.
Now suppose, let us say that we have again increased. Let us say that this page table is increasing, say fifth location, fourth location, fifth location, sixth location, seventh location, eighth location, and so on and so forth. Okay. Okay, up to, so let us say that you have 8 locations. These 4 locations, can I create another page table? I will provide that 2. So this will be referring from 0 to 3. This will be referring from 4 to 7. Okay.
Okay, sir.
Can I do that? So this will be your outer page table. This is your page table, and this is the frame number. Now I will create one more location here, saying that so if you want to 0, 1, 2, 3, you come here, something like that. Okay, like this. I will create a page table like this here for this information, like how I compress with these values. I will create one more page table here. How I created like this. The same way I'll create, see 0, 1, 2, 3, 4 frame is there, right? So this is say page 1, this is page 2. So I will keep here 1 in 1. I'll keep 0, 1, 2, 3. In 2 I'll keep 4, 5, 6, 7, 8, something like that. So if a particular 0 offset is coming, I'll refer 1. In 1, whatever the page number is 6, then, so in this case, I need two P1 and P2, two values. So what is the P1 value? Suppose I want to have this, it is in 1, then it will go to the 1. Then P2, what is the 2, 6, then it will go to the 6. Then again, it will go to the frame number. So creating a page table for the page table is outer page table. That is hierarchical page table. That's what we have shown here. Like we have an outer page table and the page of page table and D. This is the actual page table memory. Usually directly the logical address should create from here. Directly it should access from here. But now it is accessing from here to here to here. Now we need another P1 for this guy, page table access, P2 for this guy, then offset for this guy. That's what we have written here, P1, P2, D. We can create it, a 32 level, 2 level. This is one of the structure. There is no, not a thumb rule. We should keep only one page table. There is no thumb rule. You can create that. Okay, so then we can call that as a hierarchical page table, hierarchical page. If you do that, then it is called hierarchical page. Okay.
Okay, sir.
Now there is another structure called hashed page tables. So we have logical address, we have a hash function. We will store the hash function in a hash table. This hash value is mapped again and again and again. Then that particular hash value is verified. Then this particular hash value is matching. Then the physical memory is accessed. Here the R value and P value are different. Okay. The P value, we will create an hash value, hash functions. Hash, how many of you heard hash first time? Do you know what is hash function?
No, sir.
Okay. See, hash functions are a function which is one way. Okay. Suppose you have y, you calculate some value f of x. So x is some value, f, let us say that f is a hash function. Let us say that h of x. This is a hash function of x. So for given value, you will get some other value. For hash value, this could be variable size. This the properties are the x can be variable size, but the y value is always fixed size. It will compress the value. It will compress and it will give you the fixed size. For example, I will give you one example. Now, let us say that mod of, you know what is mod function, right? Modulus function. You don't know modulus function?
Yes, sir. I know.
Modulus function. So let us say that modulus function is hash value. Now, when I'm creating, say, my my x value is say 100. My x value is say 100. Sorry, 101. How many digits I have here?
3.
3. Okay. Now when I do mod of 10, that is x mod 10. 10 mod 10. What is my y value?
1.
Y value is 1. Okay. Let us say that my x value is say 10,000. 10,002. Okay. Now when I do the apply the mod value, what is my y value?
2.
So this is 2. Now maximum, when you apply this mod function, your value input is variable. It can be 1 digit, it can be 2 digit, it can be 3 digit, it can be any value, but it cannot, when you apply the mod function, the output always will be maximum 2 digits. Sorry, maximum 1 digit, right?
Yes, sir.
So this is one hash function, one example of hash function. Now I know I created one. Okay. So the variable input might be variable size. My output is fixed size. It is only 1 digit. Depends on my mod value. So all the hash functions will have this property. The input x might be variable size, but the output always is a fixed size. You can apply the same principle in computer science. Suppose if your mod is like 1 kilobyte, your values, whatever it is having, the value it will be not go beyond 1 kilobyte. Okay, if it is 4 bytes, if you are saying 32 bytes, if you are having your mod value is 32 bytes, any value you give the message, it will compress into 32 bytes only because of mod function, correct?
Yes, sir.
So this is one of the hash function. Now the properties you have to observe is the way input will be variable size, the output is always fixed size because of this value. Okay, that is number one. Number two is this function is irreversible, means you can calculate one way direction. Given x, you can calculate the value of y. X, I'll give x value 10,002. I can calculate y is equal to x mod x, so that is given 2. But from 2, I cannot create 10,002. This from I got y. I cannot create the value of 10,002. This is not reversible. From 2, you cannot create 10,002 because what is 12 by 10? 12 mod 10 is
2.
22 mod 10 is
2.
32 mod 10 is
2.
so the x value is same for many values. Sorry, the y value is same for
1.
many values. It cannot be reversible. The hash functions is one-way function. You cannot reverse it. Okay.
Yes, sir.
So there are many properties of hash functions. Now the same idea you can use. Suppose your address is having only 4 bytes or 4 kilobytes. Your hash table, you can use the hash table value. You can store this hash function, and the p value what you are giving as an input, it is not same as the hash value what you got. So you have to store this hash table and you have to verify these unique values, and if that hash value is same, then that hash value will be accessible for that memory location. Okay, so then we can call that as it is a hashed page table. Is this clear?
Yes, sir.
You can store the paging in terms of hash functions and hash tables also. Then if you are storing like that, it is called hashed page table. Then there is a called inverted page table. So you can generate a logical address PID process identifier, you can store process identifier and a particular p value, searching that, and for that particular I value you will get, that I value is will be accessed for the physical memory. Process identifier, the process, for each process identification you will store the information, not only the frame number, you store the process identification and p both values, and you are searching not one information, 2 3 information you are storing. Then only this I value will help you to calculate the physical memory. Process identifier is calculated for each process identification, right? Each process will have unique ID, PID, that we call process identifier. When you're storing process identifier and that particular process information in a page table, then process P1, P2, P3, and so on and so forth, that process identifier I value, that I value itself will give you the physical address. I value plus that, if you are storing in a sequential order, the process identification number, that I value will give you the physical address of that memory. So when we store such kind of structure, process PID value and P, we call that as an inverted page table. Usually we don't that's why I call it's inverted page table. Anyway, these are various ways how we can store the page table, hash page tables, inverted page tables, and hierarchical page tables, something like that. Now let us try to understand swapping, then we'll stop. Only 2 more slides, then I will stop. Usually, when a process is executing some instructions, the data that operates the process must be executed from the memory. So you have a main memory. This is user space, operating system space. Now CPU is here. It is taking instruction from the main memory. However, a process or a portion of a process can be swapped temporarily out of the memory to be a backing store, and then brought back into the memory for continued execution. So because your main memory is full, and you don't have any space left out, you needed some memory, but you cannot close that process. If your memory is full, you need to store this memory at some other location. We call that as a backing store. We'll put that process in that backing store, say process P1, swap out process P2 in that back store I want to load because of memory leakage, or you want to use the memory space wisely. If you are doing that swapping, swapping can be done. You can push one process into a backing store, you can bring it another process into the main memory. This will happen frequently in the operating system. Does that make sense?
Yes, sir.
Now this swapping also, you can use page tables. This backing store, you can use the page table. Suppose process A needs A, B, C, D, E. Okay. Now the page out, suppose for each process, the page out, B is stored in location 4, C is stored in location 5, E is stored in location E. So this is a page table information, right? This is looking like a page table information. So F is stored in this location. Okay. So whenever you are storing a process A for some information in that process, we can page out which are not used. Then you can bring it some other process page in based on backing store. The backing store, how we are storing the information when you are doing swapping, you can use the paging idea here also. Swapping with paging. Is this clear? The same idea
Yes,
of
sir.
paging, you are using in main memory and backing store. When you want to put it at some place, you can use a page or page in, same information with swapping and paging. Okay, so we'll stop here. This is how the main memory will access the memory and take care of many things that we need to understand. Operating system handles using paging the main memory management. When a process is running out of space, It uses swapping, using the paging. The operating system can do the hierarchical paging or hash paging, shade paging. The operating system takes care of all these things. On real life, in order to minimize effective access time, it will keep a translation look-aside buffer. Then each instruction will be replaced by least recently used or round robin approach. So these are all handled by main memory management. Okay, this is handled by the operating system. Operating system handles the main memory management using all these ideas, using paging, how it will do, that we understood. So if you have any questions, you ask me, otherwise I'll upload the slide. We will stop here. Next class, we will discuss the virtual memory. Now we discuss the main memory, we will discuss the virtual memory. But in today's class, if you have any questions, you can ask now. Okay, I uploaded the slide. Can you verify whether you will be able to see lecture 23 memory management?
Yes, sir, it is there.
Just give me 1 second. Okay, can you verify again one more time? Lecture 23 memory management is there or not?
Yes, sir, it's there.
So go through the slides. If you have any doubts, you can ask me in the next class. So we'll stop here.